Hello, and welcome to the Mechanics of Materials podcast here at Imperial College London. Today we are talking with Professor Maria Charalambides. Maria was the previous head of the Mechanics of Materials division in the Mechanical Engineering department here at Imperial. And today we're going to talk about the Mechanics of Materials division as well as how to make plastics more sustainable. So what does the Division of Mechanics of Materials do at Imperial College London?
Thank you, Michael. There are three main areas of research in our division. These are engineering for sustainability, manufacturing optimization, and fundamental mechanics research. The first one, engineering for sustainability, includes topics which are key to delivering the worldwide goal to reduce global warming and pollution. For example, we look at how to develop methods for energy storage through a next generation of batteries and hydrogen fuel cells. We optimize materials for controlling nuclear fission and fusion energy generation. We study lightweighting, which looks at reducing energy in vehicles, for example, by having lighter components, whether these are metallic or composite materials. We look at circular economy and how to minimize our use of valuable virgin material resources through novel methods of recycling of plastics, repair of plastic composites, and the redesign of single-use plastic packaging. Another example of our work in this area includes determining the optimum display and storage conditions of cultural heritage to achieve the goal of lowering energy consumption associated with climate control in museums, whilst ensuring such works of art are preserved for future generations. The second theme, manufacturing optimization and digitization, looks at how to manufacture various materials more efficiently. For example, we develop novel metaforming technologies. This development is underpinned by models predicting material microstructure evolution during forming. We are creating the factories of the future by extending the state-of-the-art in additive manufacturing, harnessing its vast potential through digital transformation and smart instrumentation. Our work extends to manufacturing of a vast array of materials, including metals, ceramics, and foods. The latter, similar to the manufacturing of engineering materials such as metals, needs insight into the microstructural evolution during production. We're developing novel computational tools for designing products which will meet consumer demands on sensory perception, as well as meet our need to produce food structures with controlled digestive performance towards improving human health. Lastly, the fundamental mechanics research theme is the backbone of our research efforts, enabling the solutions summarized above in the landscape of sustainability and manufacturing. Our division is unique as it encompasses experience in understanding and predicting performance of a vast range of materials: metals and alloys, ceramics, polymers, composites, foods, coatings, foams, gels, and adhesives. We study their behavior under impact, fatigue, creep loading, under a range of conditions, including temperature and humidity. We develop modeling and experimental techniques to enable us to build multi-scale models, linking the macrostructural makeup to the macroscale mechanical response.
The transition to zero pollution is a large theme inside Imperial College. How can engineers of materials help to achieve this goal?
Okay, so engineering is actually a fascinating field to be working in right now because of this. It is obvious we can no longer continue on our current way of doing things. We urgently need to limit carbon emissions to fight global warming and its devastating effects on our planet. Engineers are probably the best equipped profession to help solve the climate change crisis. With our unique analytical and problem-solving skills by training, we're best placed to develop new ways of energy production and storage, manufacture sustainable materials and design recycling processes, reduce waste in manufacturing, propose high-performance but lightweight materials for transport, limit carbon emissions from climate control in buildings, etc. These avenues I just mentioned are all currently researched from our engineers within our Mechanics of Materials division. It is very exciting to be part of this mission to change things for the better.
So next we'll jump into the topic of the circular economy for plastics. So Maria, what is the problem with plastics? How do they affect the environment, and what are their sustainability issues?
Plastics are receiving a very bad publicity in recent years, for example by images of oceans littered with such materials after consumer use. We have all seen terrible images of empty drinks bottles, plastic packaging, etc., swirling around in our seas and waterways or washed out on coastlines and beaches. However, we need to remember that plastics are actually a fantastic material offering several opportunities for new and optimized products. For example, they are used in food packaging in very clever multi-layered designs and therefore reduce food waste. So they actually help solve the environmental concern related to food waste. The concerns related to such food waste include the production of methane gas during food decomposition, the waste of valuable natural resources, carbon emissions during production of the food that will go to waste, and so on. Another example is that plastics are lighter than glass, so transporting plastic bottles as opposed to glass bottles leads to less energy spent during transport. So the advantages of plastics need to be kept in mind. Having said that, we need to come up with ways to use them more sustainably than what we are doing at present, limiting plastic pollution on our planet. Synthetic plastics are produced from fossil fuels, and as such, we need to limit the production of single-use plastic products from virgin polymers. We need to develop a systems approach for circular economy where technological innovations and environmental policy can work synergistically to recycle and reuse plastics at much higher rates than at present. We need to upgrade the infrastructure in waste management companies to include more plastic types and mixed plastic of smaller sizes. Finally, we need to rethink and redesign single-use plastic products such as packaging with recyclability a strict design constraint.
What's the main goal of this research project? What would a sustainable future for plastics look like?
Okay, within MOM, Mechanics of Materials Division, we're looking at various possible ways for how we can help. For example, we're focusing our efforts on multi-layered plastic packaging, widely used in packaging industries such as consumer goods, foods, pharmaceuticals. This packaging is essentially layers of different materials laminated or extruded together, each layer having a specific purpose or function: mechanical support, barrier protection against light, oxygen, and humidity. The trouble with such packaging is that because it is made out of different materials, it is very difficult to recycle and usually ends up being delegated to mixed plastic waste that then goes to either landfill or incineration, both of which are things we need to avoid if we are to move to more sustainable circular economy. So there are two contrasting solutions for this problem. Either we do not try to separate the various material layers and try to blend them together to make a new composite material that can find use in new products, or we try to separate the layers such that they can each be mechanically recycled in their respective single plastic material streams. We're looking at both of these solutions. For the route towards blending a new composite from a mix of plastics, we're developing computational models that quantify how the strength of the interface between the various materials during blending of the multi-layer plastic impacts on the mechanical properties of the new composite. This is relevant because there are various materials called compatibilizers on the market whose role is to enhance the interface between the various polymers. So for the first time, we have been able to show that we can predict what the mechanical properties of the composite will be as a function of this very important interface behavior. For the second solution, we're looking at ways for how we can separate the various layers of the multi-layer packaging to facilitate recycling in single waste streams. For example, we have designed laminates where adhesion is not uniformly applied between the various layers but only in controlled areas or patterns, leaving circular areas in the laminate where adhesion is weak. As a result of this, during shredding, which is a common step in mechanical recycling processes, if we shred to areas smaller than the imposed adhesive pattern, we will release the non-adhered layers. In addition, we have tested water-soluble interlayer adhesive, which can be easily removed during the washing stages of the recycling process. A more recent endeavor is to see if we can combine mechanical with biochemical recycling to unlock possible synergistic effects towards recycling of hard-to-recycle materials such as flexible packaging. So our work can lead to solving this specific problem related to the non-recyclability of single-use, multi-layered packaging, which make up the largest portion of non-recyclable packaging.
What kind of alternatives or solutions can we develop for single-use plastics from fossil fuels?
Most of our plastic is made from fossil fuels, gas and oil. More recently, because of environmental concerns, the use of natural raw materials to make plastics has evolved, for example using corn, sugarcane, straw, food waste, or potatoes, known as bioplastics. Having said that, there is an active debate going on whether bioplastics is a solution to end plastic waste. That is because not all bioplastics are biodegradable or if they do degrade, they do not do so more readily than fossil fuel plastics. In addition, other problems are that even when these new bioplastics biodegrade, the question is, under what conditions do they do so? Do they need an industrial composting facility with high temperatures, or can they biodegrade in the natural environment? What if they land on the bottom of the sea with no light and cold temperatures? There are also concerns that degradation into smaller particles can be a danger to marine ecosystems and water, like in the case of ordinary plastics which degrade to smaller and smaller particles or microparticles. Another complicating matter is that consumers cannot separate biodegradable plastics from ordinary plastics, and if these two are mixed, it makes recycling even more difficult than it is now. My interest would also be on the mechanical properties of these bioplastics as compared to the ordinary plastics. Can they be used for the same applications, for example? There are many questions that need to be answered here, so still a very active research field.
How can waste and plastic use be prevented and reduced?
This needs large multidisciplinary teams from very diverse fields. You cannot solve such big societal problems with a team made from a single expertise. Technological advances related to better, more efficient recycling need policy interventions to ensure that such technologies are taken up. Often, at the very early stages of a new technological advance, because of a small scale and limited initial uptake, such advances are often dearer. So, incentivization and policy become very important at this stage. Consumer behavior is also obviously a big part of the whole puzzle. But together, scientists, engineers, in collaboration with governments and NGOs, can make the much-needed difference that's needed to solve this huge problem.
How do mechanical engineers contribute to this work? Can you give a specific example?
Yeah, of course. Mechanical engineers have the right skill set to contribute in this field. They can help with bringing up answers to various problems, such as how do we redesign the packaging such that it can be more easily recycled? What potential applications can recycled plastics be useful for? And how can we improve their performance such that they do not get downgraded to a less valuable product? How can we improve mechanical recycling processes to increase the recycling rates, which are only currently 15% in Europe? Is there a clever way we can solve the problem related to contamination in the high variety in plastic waste streams? Can we get smarter sensors for sorting? If we are to reuse plastics for longer in certain applications, what materials will we need that will be more durable for longer product life? These are only some of the many questions that a mechanical engineer can get involved with.
So Maria, who is working on this project?
Okay, Michael, at Imperial we have a large team working on producing cleaner, greener plastics. We can therefore tackle this great societal problem using a systems approach rather than with isolated, focused solutions that only tackle a small area of the issue. So here in mechanical engineering, we're working on easier to recycle multi-layers packaging, as we already discussed. In chemical engineering, they're developing novel methods to enable chemical recycling for difficult-to-recycle products, such as multi-layer packaging. The advantage of such processes is that the plastics can be turned back into their raw materials, that is, their individual monomers, such that new polymers can then be made. In aeronautics, they're looking at making better use of post-consumer mixed waste using additives and reinforcing fibers. At our design school, they're developing models for understanding user perception of sustainable consumer goods. They consider the entire life cycle of products and aim to produce closed-loop material flows. In materials department, research is underway to understand possible toxicity on issues related to degraded plastics and the so-called microplastics, the small fragments produced when plastics degrade and find themselves in the human body, for example. And in our Center of Environmental Policy, they investigate policy interventions that most effectively incentivize positive changes to reduce waste generation in the first place or improve recycling rates. There are many others within Imperial, which I'm not mentioning here, also outside Imperial, that are working on solving this immense research challenge, so there is a lot of hope that we will collectively make advancements that will manage to control and reduce plastic pollution.
And finally, where does the funding come from? Are there any industrial partners or other beneficiaries?
Funding comes from the UK research councils, especially the Natural Environment Research Council. Also for ideas closer to commercialization and application, Innovate UK. This is a hot topic at the moment on lots of agendas. Industrial supporters are big packaging industries, polymer processing manufacturers, as well as industries that use the packaging, such as consumer goods and the food industry.
Thank you, Maria. We are very happy that you came to speak with us today, and we're excited to see where your research goes into the future.